The topic that we will look at today is about the use of regression model to perform classification, right? So the technique itself is called logistic regression. It is a type of regression that use variables and then use those variables to assess value as well. But instead of assessing the normal distribution values like in linear regression, what we are looking at today would be assessing the class, right? The probability, the value of the likelihood to belonging to that class. So this would be the very first model that we take on that use machine learning to capture patterns in data and then make prediction based on the existing pattern, right? The technique itself is quite popular, logistic regression. It has been used in multiple in multiple I would say in multiple disciplines, in multiple businesses. Bank use this technique, has been using this technique for I think the last 20 years to create a model to assess credit rating for individuals. Manufacturers use logistic regression to detect the event, right? The event that could occur, right? And there are also others disciplines that make use of this type of classification in order to identify the potential of the data of the individual of the unit of analysis belonging to that class. Okay, so when we talk about machine learning, the root of machine learning is based on statistics. And this is one of the predictive model in statistics that has been employed widely in the data science research area since back then. Okay, so today we take a look at this in the general sense and in mathematical sense, which I borrow some of the material from the master degree class I taught last semester. Just a few slides, and two graphs on continuing from last time that we take a look at the way that you can estimate the parameters of the model, right? Last time we look at a least square, right? This time we would look at gradient descent, another technique that you can optimize for the parameters, and it has been used in this logistic regression model. Okay, so let's go. Let's move on. So today we would look at the background, general description of the logistic regression, the generalized linear model, which is it is the combination of the models, including logistic regression, linear regression, that you kind of describe them as just one package. And logistic regression technique itself, right? We'll take a look at that, and also with the data that I have, you can practice along the way, or you can try that afterward when you review it with the video that we have here. All right. So we have taken a look at the regression. Okay. Last week we looked at linear regression. Linear regression is a technique that you can explain relationships between variables, between input variables and the output variables. Multiple regression associate variables, a number of variables, to predict one variable, right? You kind of create linear regression with multiple input. But sometimes the response can be not normal, right? They can be like categorical. They can be this categorical. They can be the cow data. Let me change this into laser pointer. Can be cow data or categorical. So it depends on the types of the input. The regression would need to be changed. Otherwise, the epsilons or the errors that you try to control, the line should pass through the middle of the data. That distribution of errors depends on the distributions of response, right? So if the response distribute not in normal distribution way, right, there has to be a technique that allow you to modify the relationships and capture the patterns not in normal way but in categorical way, okay, or in count manners, right? So when we talk about categorical target, right, we can the target itself can be applied to different types of applications, right? You can create a model that predict success or fail, right? Whether you would success in attempt to convince customer to purchase your products or fail to do that, whether you success to perform the task or fail to perform the task, whether you would success in right creating this project would be success or whether this project would be a failure in the investment term. So this is one of the thing that is possible. It can be yes, no, right? Yes in terms of the event would happen, no in terms of the event would not happen, which the event I'm talking about is quite flexible. It can be lots of things that you can label it with yes, no. It can be like yes, no in terms of the label. For example, if you create a model that take in text data and then it would tag the text data with the specific tagging, like whether this is drama, whether this is about politics. You are trying to do like creating a system to perform topic classification. Then your tag can be yes, no, right? It can be tag or not tag, right? In terms of classification. And you can imagine further that there are plenty of applications that you can use classification to take on now, right? It can be for telecom company or for the subscription company. Right now, business, software business run on the subscription model. You know that, right? When you play games, you kind of subscribe to the games. You have there are certain way that you need to pay for the games. When you purchase software, right? You have to pay it regularly, maybe every month to do so, maybe every years. Churn is an event that a customer would leave the company, right? Would leave the company, would terminate the contract, maybe because of the price, maybe because of they do not want the service anymore, or maybe because of the problem. So there might be different and various reasons underlying that. The churn event is one of the important applications in data science when you try to model and capture behavior of customers. Okay, you can predict whether for banks, default here doesn't mean default setting. Default here means where the customer does not pay, right? The customer does not pay, so the account can be the status of normal or default, right? There's a problem with that, not paying. Or you can try to predict the trends, whether the trends of data would go upward, downward, or normal. In that sense, since there are multiple category, multiple targets, there are three classes, right? Downward stay the same, and upward. Then you can create comparison systems. Like instead of having 3 classes, you can have like this one, 2 classes, upward or not upward, right? Or downward or not downward. And then you can create a comparison between them. This can be applied to other things as well. For example, in text analysis, when you take in the data from Pantip, from Twitter, from Facebook, and then you have text data. You might want to predict whether this text data is positive, not positive, right? Positive or not positive, or negative, like or not negative, right? So those are the possible label that you can make predictions, and they will be represented as the targets, as the Y. Okay. Since the data itself is not values, right? You cannot create histogram distribution like that. So the distribution, so to explain distribution for this one, you need to use the binomial terminology. Like you need to think about the proportion of things would happen versus not happening. and there is measurements that allow you to do that. That measurement is called an odds, right? An odds. An odds is the way that you're trying to explain the chance that thing would happen, right? In the quantitative sense, and one thing would happen versus not happening. You would win how many? 5 to 1. That is an odd, right? An odd is calculated from from the probability of the event would happen, that the event would occur, divided by the probability that that event would not occur. So you can see that an odd is a proportion between a chance that things would happen versus not happen. Okay, so it's PE divided by 1 minus PE, basically. Okay, so if we talk about the frequencies of things would happen, you have like X would happen, and it would have it would happen X time, not happen Y time. You can calculate the odd like this one, that we have X over X plus Y as the probability of E would happen, and Y over X plus Y as the probability of E not happening, right? And then we have the odds. Right? But well, we are not going to calculate odd directly like this one. Okay, but let's take a look at the data and think about it in terms of odds, right? So what are the odds value for each of these each of this job in terms of this bank data? This bank data is the data about the customers accepting offer, right? I think you saw this one already, and then we also have that in the midterm exam. So you explained that already somehow. We have Y as the Y here as the output, the response, whether customers would respond accepting the long-term deposit, long-term plan in terms of deposit plan or not, right? And then we have the predictors, X as job here, and then we're trying to see distributions in terms of the job versus accepting and not accepting. All right, so let's take a look at the program, and then we will take a look at the odds of different jobs, whether they are independent or dependent. So there must be certain relationship between them, right? Let's take a look at it. Right, I'm going to switch the share to this. Right, so start with loading library. And then I'm reading data in. Note that separator here is pipe. Check if they're okay. Oh no, sorry, it's not pipe, semicolon. Right, now we have the bank data. Let's create the cross tabulation of this data set by using table, and the first variable will be the job. The second one is the Y. Now we have the number, or if I refer back to the prior slide, is the X and Y, right? Is X and Y values, X and Y number, and that is in that. You can use put these yes and no into X and Y, and then you have a chance. You have the odd values of different job here, right? Okay, so let's put it in calculate it directly first. Okay, say we have 631 divided by 4540, right? So the odds of the odds of having job admin and accepting the offer would be 0.138, 0.138, or in a a simpler term, you can think about this as dividing this by this one, 4540631. So you have about 7 to 1, right? So you may have heard this term before, like you may have 7 to 1 odd, right, between the two chance, the thing that will happen. This as well, I would say it's like 1 to 7, right? This is 7.1127, meaning that out of 8 people, 1 people would accept would accept this offer. Right? So you may have heard this notion before, like out of a number of people, there would be 1 people who would do that, 100 people who would do that, right? So here is the way that this has come from, right? So it's the odd between the two events, right? So let's look at it further. We can just select and see the distribution. In this distribution, it will show us the associations between the variables. You can see the associations between categorical and categorical variable through this distribution. And for the categorical variables like the y values and the age value here, numerical variable, this can be we can find association by using distribution like box plot, and then we can see if there are distributions associations between variables or not. If these two blocks are far apart, that would mean that age associate with y, or in other way around, y associate with age, right? Between the two, they are quite equal relationships here, right? So we are not going to look at this today, because what we will look at is the so this is the relationship between categorical variable and the numerical variables. You can see that in terms of categorical and categorical, when we look at the way that we calculate odds ratio, the odd values, we have this: if you get a job of admin, you have a chance of about 7 to 1 to accept offer, right? But if you are in the retired stage here, you can see that the chance increased to 3 to 1, right? Because it's 1700 and 500, right? This is 3 to 1. If you are a housemaid, this is 10 to 1. Right? So there are difference. So you can see the differences in terms of the chance, the odd values between different jobs, and this indicate association between jobs and the chance of accepting the offer. Logistic regression would take in this and then create a relationship between jobs and the chance of accepting the offer, the odd between x and y here, and between no and yes here. Now, when we talk about the association between variables, we also have association between numerical and categorical variables here. Numerical in terms of age, you can see distribution are different here. That means they are also relates to y, right? So you can see associations associating with category in 2 different ways. The way that you pull them together and create relationships, that can be done through regression. Okay. So how do we assess that they are the relationship exists in terms of the categorical variables? I'm not going to calculate this because we have already done that before the midterms. This is through chi-square statistics, right? I'll go through it quickly. In chi-square statistics, you can calculate associations between variables by comparing the observed and the expected. Right? If the observed differ from the expected, then there are associations between variables. Right, like this one. This one has weak relationships because the expected distribution here are similar to the actual value, the observed value. Okay. And for strong relationship, because there are difference and you calculate chi-square and it is more than 1, actually it is far from 0, sorry, far from, not more than 1, far from 0. That means this value matters, and that means there are differences between the actual distribution and the expected distribution, and then that indicates strong relationships. Okay, we have chi-square here. The way you can calculate chi-square in the R by using by creating the cross tabulation. The results of this line will give you cross tabulation, just like the last example. And then from this cross tabulation, we put this in as matrix into the chi-square, and then chi-square would associate the association between row variables. I put it as VR, and the VC, the variable in column, variable in row, and it will associate association between them. You can see that Marito and Y, there are certain association between them through this assessment. Okay, so chi-square test allow you to assess association between data, right? But you can see that association can be described that way, right? You can see that, and also you can see that there are relationships between age, job, to the subscription, to accepting the offer. Okay, but how do we create model? Right, suppose we roll back to linear regression and set like no to 0 and yes to 1. Right, we set no to 0 and yes to 1. Can we just do linear regression? The problem is, if you do the linear regression by setting no to 0 and yes to 1, there will be values and errors that is more than 1, more than 0, because linear regression does not have limitations that the predicted value have to be between 0 and 1. That means you need a way to like compress the output so that the output can be only through that specific range, to that 0 to 1, right? When we think about it that way, and when we look at the distribution itself, you see that this yes and no, right, they are from binomial distribution. So you can explain it in terms of the probability, and we will try to find associations between the probabilities and the variables. Okay, and this technique is called generalized linear model. Actually, it's called logistic regression, but to kind of encapsulate everything into just one model, the regression, the whole regression can be explained in terms of the generalized linear regression model. Logistic regression is one of the examples, one of the special case of the logistic regression. Linear regression is also one of the special case in the generalized linear model. Logistic regression is a special case in the GLM as well. Okay, so how do you explain the GLM, the generalized linear model? Right, there are characteristics related to the generalized linear model. The first one is that the distribution, you would need to have probability distribution that explain the outcome variable. For linear regression, that will be normal distribution. For logistic regression, you have binomial distribution, which how it works we will see later on here. And you need to have a linear model, otherwise it wouldn't call generalized linear model, right? You need to have a linear model like this one, multiple variables associating with a type of value here, a new value. And then you need to have this link function. The link function would map from the would say from the outcome for new here, the results of linear model to the distribution of the variable. So it means that you have a certain way to map from the actual response to the regression model terms. Okay, for linear regression, that link function is just one, right? What you have is what you get, right? That's for linear regression. But for logistic regression, we need to use a function that can represent probability, that can represent the associations between the chance of things happen and things not happen. And that function is called the logistic function. Right? The logic function is used in logistic regression model. The logic function calculate the probability between things happen and things not happen, right? The ratio between the probability, and then take the log of this ratio, and then from this log ratio, we will associate this log ratio with the linear regression model. All right. Why doing that? You may wonder. Okay. So if we have a line here, let me use this to explain. Right? If we have a line here, right, and we have a line and the data, suppose they belong to the two classes. This line can be explained as y equal mx plus b, right? You know that this is like a line equation, and for m and b, these are the value that we have in the in the last lecture that we have. Okay, and for this y equal mx plus b, last time we used this line to explain the trends between the data. But this time we are going to use it to divide the data into two classes, one class and another class. However, when you take a look at this one and then put it into work, for certain m and b, right? For certain m and b, the line can be this, or it can be something like this. So you can have different lines separating the data, but which line is the best one? And when you calculate the values, right? When you calculate the value here, certain value of x, say this one, certain value of x here for this point, you see that this point is under the line, right? It's under the line, and what would happen if you calculate y using this x, right? The predicted y would be this. This is y hat, right? The value that you get, which when you compare that to the actual y, this is the actual y, you see that it's not on the line. And I think you have learned that in the mathematics course, that for points and line, if the point is on the line, then the value that when you put x, what happened? Okay, when you put this into x and y, when you put the point into the x and y and then make calculation, if the point is on the line, then it means that the equation would be satisfied, right? You have the value combined equals 0. I think you remember that the point is on the line. But if the point is under the line, what would happen? Right? If the point is under the line, then say we have, if we move it like that, we would have this equal y minus mx minus b, right? If the point, this is the case that the point is on the line, right? But if the point is not on the line, say if it's under the line, then you would have this value less than 0, right? Right, this value would be less than 0, right? The value that you get here, fx, right? Fx would be less than 0 in that case if it's under the line, right? So you can see that you can from the value that you calculated, if you have the m and b trained and you put the value of the points into the lines, let me get that a bit. ทำไมไม่ปิดประตู Right? If the point is under the line, then you would have the value not equal 0. Okay. The problem is the point can be as far off the line as it can be, right? It can be it can be very far from the line, and you would have the values not in the range of 0 and 1 as the class, as the value that you would have there. So what to make use of that? You can see that for the length from the point to the line here, it would have the range up to minus, from the minus infinity up to infinity, in that sense, right? The range of the value here. And if it's on the line, then it will be 0. Right? So put it this way back here. You have the value range from minus infinity to 0 to infinity. Okay, so that means the data point can be as far from the line as it can. It can be on the line if it's on the boundary, or it can be the upward, right? If it's belong to, say, under the line, you can say that, okay, this is X or this is O, right? You can use that to make classification. But sometimes we want to find that in the probability way, not just in whether it's whether it's above the line or below the line. That is actually a technique that a machine, I would say, the classification model that has been used maybe 20 years ago. This is called the LDA, linear discriminant analysis, right? Linear discriminant analysis create a model for doing classification, just like what I explained here, that it take a look at whether this is above the line or below the line. But because linear discriminant analysis or the technique like this one can just put, you cannot use it in terms of the associating with the proportion. You cannot find probability, right? The range of the value can be as much as it can. So there's a problem there, right? You don't have the absolute values. You don't have because all the values are, as I said, you don't have the relative value that you want. Probability is relative value. And in order to make assessment, in order to make judgment, sometimes you want the value in probability terms, because you want to know what is the chance thing would happen, not just that it has value, right? Whether is it high chance 0.9 or low chance 0.1. But in the case that we have here, you have only like there's a above the line or below the line. All right. So instead of doing that, we can transform the minus infinity to infinity by using this one, this thing, right? What is this, right? This is called the log odd, log odd. This is an odd inside, and you take log, and what would happen to the log of odd? We know that probability has the value between has the value less than 1, right? So what would be the range of p divided by 1 over p? Can anyone tell me here? P divided by 1 over p, what would be the range of value? You can put it in chat. The range of values of p divided by 1 over p. Think about that. P would have p itself would have the range of 0 to 1, right? And p divided by 1 minus p, p divided by p over 1 minus p. What would be the range of this value? Think about if p is about 0, almost 0. If p is almost 0, then the value would be what? If p is more than 0.5, so I would say here for this, you have the case that p approached 0, p is about 0.5, and p is more than 0.5 to 1, right? What would happen? Minus infinity to infinity. Incorrect. There is no that wouldn't happen. 0 to infinity. Yes. But another important part, this is correct, it will be 0 to infinity. But there will be different range, right? Between 0 to 0.5. Between 0 to 0.5, the values of this ratio will be between 0 to 1, right? Because 0.5 divided by 0.5 equal 1. If the numerator has the value less than 0.5, then you have the value less than 1, right? Once the value of p is more than 0.5, then and this point on, then you can have the value as high as infinity. Okay, so the odd value looks like this one. Okay, it's distributed this way. When you take the log of odd, right? Log odd. Now the range should be differ, because logarithm of 0 equals logarithm when the value of inside the logarithm approached 0. What would be the value of? Yes, right, it would be negative infinity. And then log of 1 is 0, and log of whatever large value there, you also have infinity there. The important thing here is that the growth here is more of the exponential, while this would be linear. Again, this is like more of compressed exponential, and this would be linear. Right, so and that means in the realm of log odds, the values of log odds will be linear values. And you know that once you have linear value, you can associate linear value with the linear equations. Thus, we have the generalized linear model for logistic regression. Okay. So let's go on here. Let me clear the drawing. Okay, you will see the detail for sure later on. Let me finish it. Start. Did I should turn off? All right. Okay. Logistic regression, right? So when to use logistic regression? Logistic regression is a very old technique. It has been used for quite a while, but it's still widely used today. Why is that? Because the technique itself is quite suitable when you have large feature, right? A large number of features. You have to associate which features are important, and then you can use them in here. But there are, because it is regression is based on reduction of a large data set into just a small associations. Doing that allow you to express relationships in a simpler equation manner. It is also suitable for large observations, because you kind of reduce the variations in the large observational data through relationships between variables in the equations. It has been used in many places, in the banks, in the telecom, in lots of auto way. When you want to find relationship linearly in terms of the data itself and the response. Okay, now let's look at the mathematical foundation of the logistic regression. When we talk about logistic regression, we essentially have linear model, right? But because it is not entirely linear, because y is not distributed in linear, so I explained it as this nonlinear regression model. You have regression model you want to find association with, but because of the distribution, it's not entirely linear model. So you have this fx, y can be explained by this fx beta, but fx beta can be nonlinear in this sense, because if you think about that, you have the log odd, right? That means the value itself, the y value itself, is not the actual values, it's the proportions. So it's not distributed normal distributions, right? So we cannot use least square. Basically, we need to use a better optimization technique that is actually a foundation of deep learning to do the job. Beta here would be the parameters that we need to estimate. That we need last time we need to calculate partial derivative of all of that at this time as well, right? And epsilon here is the random error that should be normal distribution, mean 0 and variance sigma square. Okay, in the nonlinear regression we have observation y and a bunch of x, and then when we express this in terms of error, it will look like this one, that the error function would be the values, the actual value, minus f of the function of the regression that we have here, right? Fx beta and then square. Right? This is the error, the difference, and square indicate the square of error, and the summation, which will be the combination of the error. So this is like the sum square errors entirely. And from this one, we will find the beta. Because values here will change according to beta, we will find beta that is the most suitable. This is for last time, right? Linear regression. However, if the function is not linear, right? If the function is not linear like this time, we have a problem. A problem is that the lowest point might not be you can find like there might be like multiple lowest point. So if we take the partial diff and solve equations, there will be problems, because the error planes might be complex and the lowest point may be multiple values, and that's a problem. And you may have the situation that you encounter with unsolvable roots, or it is too complicated. It might be solvable, but it is too complicated to calculate. Like this one, you take derivative of this one, you get the same, right? You cannot set it to 0 because the value is 1. So how to address this problem? Okay, there's the technique called this gradient descent. Imagine that you want to go down the mountain. Right? When you want to go down the mountain, you wouldn't just jump down the mountain because you would not know, right? Suppose that you can, if you know where it is the lowest point, you can maybe jump. But if say there are lots of trees and then you see only the path in front of yourself, that there's a certain path go down, a certain path go up. Right? Which way would you go in order to go down the mountain? Right? That's the idea of gradient descent. You are trying to find the gradient. Right? The gradient is the direction that when you change the values of variables, the value of function will change according to that direction. Right? So suppose that we have this fx and we are at this point. Do you remember in the mathematics class, there is one problem, intrigue problem, that asks you to find the tangent of the specific point on the line, right? You might remember, right, that in that problem you kind of having this function, and then you have a point, then you have to find the tangent vector at that point. That tangent vector is actually the gradient, right? It comes from the derivative of fx, or in other words, this is the slope. A slope at that specific point. It will tell you that once you change the value of x, then you change the value of x further, then this value of fx would increase or decrease. So it tells you the direction of this change, right? From this direction of the change, you can make guess on which direction you would go to in order to go down to the lowest point. So if at this point we find that the gradients go up, that means when you increase the value of fx would go up. Then what would we do? We would go to the opposite direction of the gradient. So the next step would be on the opposite direction of the gradient. Once you reach that step, we will form estimation of the new gradient again, and then go into the opposite direction. Then calculate gradient and go into opposite direction until the value of gradient reduce to 0, or until that you reach the point that you cannot go further. When you go further, the value of function increase. So this is the basic idea of gradient descent, right? At each step, we would estimate the gradient, the tangent, which in mathematics, in your mathematics, is it Math 2 or Math 3? I don't remember. It should be, or Math 1. It should be Math 1, I think, or geometric Math 3. I don't remember exactly that. But yeah, there they are. Right? You can see that, well, this make use of the mathematics that you learned. So the process of gradient descent start by randomly guessing a point. Just one point, you can just randomly choose one out of the whole thing, right? Just one point, which means 1x, and then you get this point. Then repeat the step, right? First by estimate the gradient, choose the step, and then go the opposite direction of the gradient, right? Update. Then keep doing that, right? Until you reach the destination, or until the stopping criterion is satisfied. So what are the stopping criterions? One of which can be number of iterations. Second can be the size of gradient. If the size of gradient reduced to a very small value. Another one, the third one, can be that the error increased, right? If the error increased, then that's the stopping criteria. Okay, this is the technique called gradient descent. Okay, so what does it mean by this in terms of our model? So it means that we need to randomly guessing beta first. Once you guess the beta values, then At that point, you can associate, right? We need to take partial derivative of the error function with respect to the parameters, and then substitute the value at that point, right? We have the value at that point. I should put it here like this one. Take derivative or guessing beta, then you get this like beta 0, and then you have to substitute after partial dip, you have to substitute beta equal beta 0 because you have that beta, and then go on and then choose a step size, and then update from beta 0 to beta t plus 1, and then keep doing that, right? Keep doing that until you reach the stopping criterion, which is the derivative itself is approximately 0. Or it can be you reach maximum iterations, it can be that the error increase. Okay, this is a technique called gradient descent. Now we'll take a look at how gradient descent is performed to address the problem of logistic regression. Right. The TA would laugh right now because this is actually the slides from that class. From the last year master degree class, but so these two slides is just to show you how the partial dip is done for the gradient descent. If you do not grasp the idea for this one, don't worry, right? In your exam, in your evaluation, I would not ask you to do this, right? But I want to just let you know that this is the foundation of how the function in R obtains parameters. Okay, if you still like these things, you can study further in machine learning, in advanced data science, in deep learning, then you encounter this for sure. I will teach this next semester as well in the deep learning course. So let me switch to iPad. That means it should allow me to share content. No, only the host can share. Okay, I make you host. Okay, so from what you see here, maybe I should just doing this. Sorry. Because yeah, I'll just annotate through this because this is not like the requirement for you guys. You are just second year students, undergrad. I would not expect you to understand all it, but if you are into this, I would challenge you to understand it more. Will allow you to get a nice grip on what exactly is machine learning, what exactly is deep learning, and so on. Okay, so in terms of logistic regression, right? In logistic regression, we express in logistic regression, we express the associations between the chance of things happen and not happening in terms of this equation. We have this hx as the logit function, which is in this form. It's 1 over 1 plus e to the minus fx. It's fx. So and this is the same as in this. So you can associate the value of fx with hx. And now it's actually locked here. It should be locked here. Okay, I missed that. So when you take these two, it can be derived as this, right? It just takes exponential, and then you'll see, you can try that yourself later on. Right, so I can just show you here. So you have h theta x over 1 minus h theta x equal e to the fx. And then I will just switch place. You have h theta x e to the minus fx equal 1 minus h theta x, and afterward just put it together. You have 1 plus e to the minus fx hx equal 1, then you get this one. All right, so this is how you associate the regression to this. This is called logistic function. Logistic function. There's nice property with the logistic function, in a sense that when you let me clear the screen first. Right, when you make derivative of this logistic function, the derivative will be the value of the function multiplied by the 1 minus the value of the function. Why is that? 1 over 1 plus e to the minus fx, right? This is gx. If you make or this would be curve, right? Because we just want to know about theta. Hx itself is this function, and fx is this function. And suppose that we I've mistaken in minus like this one, and we know that fx equal theta 0 plus summation of theta I xi. All right, and if we were to calculate the partial derivative, this is gx of curve of gx by curve of theta, it would be the partial diff of this function. The partial diff of this function will be what? If you take the derivative of this theta 1 over 1 plus minus fx, this means you take derivative of curve of by curve theta of the 1 plus e to the minus fx to the minus 1, right? And that would be equal minus 1 times 1 plus e to the minus fx to the minus 2, and then you can take derivative of the inside, and that would result in curve of e to the minus fx by curve theta, and partial derivative of this would result in minus of I should be this way, minus of 1 over 1 plus e to the minus fx and curve e to the minus fx by whatever give you curve e to the minus fx and curve of fx by curve theta. Because it has minus, I will just put minus in front here, which give you plus, right? So what is curve fx by curve theta? say you take a look at this. Suppose we talk about certain set theta I. This would be well, I run out of the space. I did not use the whiteboard for sure, so that's the result here. So let me put this, continue here. So once we have that, we would have e to the minus fx over 1 plus e to the minus fx square, and curve fx by theta equal to xi. The reason is because when you take a look at this, there's only one terms related to theta, that is xi, right? When you curve by theta, that would remove theta out and you have only xi remain. Just like when you have like dip of 2x, you get 2, right? Dip of 2x by dx, you get 2. Treat 2 as constant and then x as variable, you get only the constant. So when you make partial derivative, you treat the rest as constant and just doing the same derivative to the variable that you are interested in. And in this case, it's theta. So that means theta x would result in just xi. And when we arrange it a bit, we would have this form because we have like 1 over 1 plus e to the minus fx, right? Time e to the minus fx. Yes. Do you have any things to say related to this? No? Good. 1 plus e to the minus fx here. So and time xi. Right. So this is it. The first one here, let me use another color. The first term is hx. And you can find out yourself that the second term here is 1 minus hx. And the last one is the xi here. Okay, so the derivative of logistic function give you a nice properties that you have the same form, right? You take derivative of h theta xi, you get h theta xi times 1 minus h theta xi times xi. Right? So this is good because in this sense you don't have different form. You just have just that one function multiplied by 1 minus that function multiplied by x. And then you get the derivative of the function. Okay, so this is good, right? That allows us to make calculation easier. Okay, so now let's take a look at the error function of logistic regression. Okay, I will clear the screen. You can review that later in your video. Right? So that is how you can see that the h theta x, when you make derivative of that, it results in a simple multiplication between the function and 1 minus the function values. Now, what is errors in logistic regression? Right? Error in classification. In the linear regression, the error is the square error. Like in linear regression, you have the square error. Sorry, I should say you have the sum of square error, SSE, sum of the square error. However, in logistic regression, since the value itself is not the aim is not the value, the aim is in terms of the proportion, right, the class. In order to represent the loss in terms of making wrong classifications, mathematicians come up with a nice way to explain that. This is called cross entropy, loss function, cross entropy. What is cross entropy, right? This cross entropy is the You see that you take in the value of y, and then the value of 1 minus y, right? Y is the value of the class. Say y can be 1 or can be 0, right? Y is 1, then you have hx, which is the results of the model. If you are predicting the positive class, the log hx should be large value. If it's large value and y is positive, then this would be negative value. But if it is on the other way around, right? If it is this one, if y is 0 for that class, then this term would be approximately 1. If yi equals 0, then this term would be about 1, right? And then this part indicate the probability of not of the negative class, I say negative positive class, right? This would be the pop of positive class, right? And this is the label of positive. But it's not actually the label of positive, because the y value is the values that at that moment, right? You can have x and y, and if that is not correct, what would happen? Suppose that the y itself is 0, right? Y itself is 0, but this term is large. Suppose in this situation, y equals 0. Y equals 0, but this is large. That's a problem, because if y is 0 and this is large, you will see that 0 times large value equal 0, right? And if this is large, this one will would be small, and this one would be 1, right? For 0 class, this is misclassification, right? In the sense of wrong classification, in the, or should I say, not good, not fit, right? Not fit or not good case, right? If you have this is when the model is not good, it would mean that the h theta x would give you wrong value. So instead of giving you low h theta x in the case of y equals 0, it gives you large value, and you will see that it will give you very small, right? In total, this would be a small value, okay? A small minus, right? So that is not is a case of not good. So if it is good fit, then let me clear it here. If it is a good fit, say we have y equals 0, this one should be small, and this one would be 1, this would be large, and 1 multiplied by a large value, you get a large negative value, okay? And now you can see that here is the loss function, right? We want to minimize the, we want to make this loss function as low as possible. And when you make it as low as possible, it means that this has to be as negative as possible. And that would make the value of theta, the value of parameters, at the base value there. So to do so, you need to calculate the gradient. The gradient of that function can be done through this. I'm not going to do that for the undergrad. Just if you are interested in how it is done, you can follow through this later on. I will just make note here to show you the continuation. We get like this j theta by theta, and dip of the because this is this would be when you encounter like summation, the partial dip would be moved in into this, right? Because y doesn't relate to theta, and dip of log results in 1 over the function, and you have the diff of the inside further. And for it also goes for this one diff of log, you get 1 over 1 minus theta h theta x, and diff of the inside, and then calculating further, deriving further of diff of the inside by theta, and we end up with this one, right? Why is that? Because we know that diff of theta h theta x is h times 1 minus h, right? H times 1 minus h and then x, right? This is the dip of hx that we h theta x that we looked at earlier, and the same go for the other one. Okay, and just the remaining is just arranging it into the form. So finally, I'll just go to here. At the end, the result is quite simple. That is the gradient of this cross entropy equals to the predicted, right? The predicted value minus the actual multiplied by input, and then sum them all. Then you get the errors and you get the gradient of this, right? So the predicted minus actual would tells you the direction, right? Whether you kind of overestimate or underestimate, then you can adjust. And then x would tells you whether you are actually right now going up or going down, right? In positive or negative realm, right? And then by multiply them all, you know the direction of the change, and then you can use that in gradient descent. And in the gradient descent, you can update the parameters by adjusting the gradient by multiplying certain small values and then adjusting the parameters. That's it. This is the gradient descent. Let's and this is what I did from the formula that I derived to you guys. I write an R code that starting from creating random like this one, and then starting from random m and b, and keep adjusting m and b through iterations that you can see here, and then updating the parameters in each iterations. You can see that the line now kind of change, moving from wrong position into the proper position that it would separate the data into two classes, right? So this is how logistic regression is done. Okay, but we are not going to do it by or from scratch for undergrad, right? For undergrad level, you will use a tool to perform that. But I would challenge if anyone really like to want to take into want to do what I did here, you can try and show me results later on, right? I'll be impressed. But nevertheless, I would just ask you to do this, right? In the lab, you don't have to do this as well. You don't have to do this. In the lab, you can just using R library to do that. And in R library, we will use the GLM, the generalized linear model function, which allow us to fit the data into a linear model, right? Okay. In the second part here, we are going to learn on about how to write a code that could create logistic regression model through the GLM functions, right? To the generalized linear model function. We just like the last time we used LM, linear regression, linear model function. GLM is more like the name suggests, that the more generalized. It can be applied to multiple types of the link function. And this time we'll use the binomial link function in the family binomial, and creating the logistic regression model, right? So we can fit the model to the data through this. Okay, I'll just switch to R then. Right, here we can create a model by using model and then GLM. Alright, you can see the GLM function first. Right, this is fitting a model to the using generalized linear model. The help indicate that you need to have like formula and then specify family. Gaussian family means that you are creating linear regression. So we have to change that, GLM, and then you need a formula of the model that you want to create. Right? So this would be, we want to predict y, tilt, and then using the variable job plus age, and the data would be the bank data that we have, and family, this would equal to binomial. Now we use binomial family. The binomial family indicate the, so I'm going to show you here is that when you click at this family objects, you can choose between binomial, Gaussian, or Poisson, if the data itself is Poisson distribution, or if it's the like inverse Gaussian, gamma distribution. So there are multiple types here. What we will look at would be just the binomial using logic link function. So just like this, and here you have already created logistic regression, right? Just, and the underlying mechanism would be the similar way that I show you. Might be different depending on the detailed algorithm that they use, but nonetheless it is the same. Then you can, oh sorry, this is Python style. Summary and model. Right. Looking at the summary of the model, this will give you the call, which is the way that you create this model, and it will give you the residual, right? Just like in linear regression, give you the residual. Here you can see associations between specific levels in the model, right? So it actually, GLM actually separate your variables, the job variable, into levels, and for each level it associates the level itself, whether when you have that level comparing to not having that level, and having an estimate associated with the y. The negative value indicates lower chance, positive value indicates higher chance. So to interpret this, you can interpret it like this, that is, if the estimate, the coefficient is positive, that means it is the level positively associated with customer accepting the offer. On the other way around, if the values are negative, that means the job job level here associated with not accepting the offer. So we can see here that like blue collar housemaid, like what we saw earlier, that the chance is like 10 to 1, 10 to not accepting, right? And you get negative value here. But the retired students are accepting offers, right? So from the parameters of logistic regression, you can know, now how the associations between category would associate with the chance of customer accepting that. And also here, age doesn't matter. It tells you here that age doesn't matter, does not relate to accepting the offer when you have the job already, right? So these are so from the data here you can interpret the results. And let's go back to slide, right? And you can make prediction by using the function predict. Okay, the function predict allow you to make prediction using the model and using the data that you have. Oh, sorry, it's bank data. And then it will predict the results here. But please be careful here because unlike linear regression, the value that you got from prediction, here would be at the link level. So what do I mean by that? Right. So now let's look at this predict.glm. Okay, this is the prediction function for GLM object. Predict.glm will give you the response, right? The values. Let's see. It will give you. So there's this type, the type of prediction. Okay, the default will be scale on the linear predictor. That means the value here that you get is in terms of the linear predictor. The value will be from minus infinite to infinite. Now, when you create a model for logistic regression, what you want to know is actually the probability of belonging to that class, the probability of accept, the probability of yes, the probability of fail, right? You want to know the probability. To get the probability instead of getting the linear value here, you need to change type into response, right? Once you get type to response, it will give you predicted probabilities. Okay, then we need to change this type to response, and then here it gives you the probability less than 1. You can see that in order to make use of the functions, in order to make use of the code here, you need to understand the core mathematics of the model. Otherwise, you wouldn't know what are coefficients, what would be the parameter, what would be the probabilities here, what does it mean by linear scale here that it explained in the help. So working on data modeling, working on data science, you probably need to delve into mathematics, into statistics, and then make use of the things that you learn, particularly in the undergrad levels, foundations, to interpret the results here. So once you get the prediction, you can see that the prediction will give you the value like 0 point something. This value is the probability of accepting, right? Probability of accepting the offer. Now, how do you know whether 0.11 or 0.07 or 0.22, which one indicate that customer would accept the offer, right? How would you know, right? It traces back to the thing we learned before the midterm. It's called prior probability. Prior probability is the probability of the class happen, right? Without any adjustment, it just happened, right? Like the chance that the customer would accept offer, and that comes from like if you create a table of the bank data $y, right? And then use, thing is you can use scale, right? Or is that Python? I suppose that is Python. Right, it kind of becomes confused between the two then. N. No, that's just Python as well. So I just use something like this. Then you have 5289 divided by 5289 plus 39922, and that is 11%. That means the prior probability is about 11.7% or 0.117. So if the value is more than 0.117, then it means that in your prediction there's a chance that the customer would accept, right, more than normal distribution, more than the usual distribution that you have. But if the value is lower than 0.117, then it means that it kind of having less chance. You predict that customer might not accept the offer. You may predict that. Okay, so here we can make prediction, right? Since we know that 0.117 is the key, we know that the class is imbalanced. We can make prediction by saying that suppose that is more than 0.2, let it be yes. If it's less than 0.2, let it be no, right? And 0.2 is actually more stringent, right? More stringent means that because the chance of accepting offer is only 0.11, but we say that it must be more than 0.2. That means we want to eliminate the chance that you will make wrong prediction. Okay, so here we need to change it into the yes and no so that we can compare with y. So let's first we can reach res, and I will use this res c. Done this later on. Use if else. If res is more than 0.2, then you get yes. Otherwise, you get no. Right, we get the result here. Then convert it to factor, and we have res class. Then we will compare the result. Right, the way to evaluate the results using because we now have this res c, right? This res c is the class, right? Yes and no class, just like this bank data $sign y, they are also class here. So now we are going to compare the results. We haven't separated data into training test yet. You can see that. We'll do that later on in a simpler in next lecture. Res c and y, and we can evaluate the results by creating this. This is called confusion matrix. Oh, sorry, I need to switch it back here. Right, we need to compare the actual with the prediction, right? And this inside the box here would be the number of correct prediction in positive sense, correct prediction in the negative sense, the wrong prediction in the positive sense, and wrong prediction in the negative sense. Right? We call this true positive, true negative, false positive, false negative. Right? Now, let's compare this to something that is serious right now, like in the coronavirus testing. True positive, right? This is like model says true, or the test says true, and you actually have that. True positive would mean that the test indicate that you have been infected, right? True negative would mean that the test has confirmed that you are not infected. Okay, so that makes sense. Now, false positive in the coronavirus testing would mean that the test indicate that you have the virus, but in fact you are not having that, right? So there will be problems, and usually false positive would occur a lot. So that's why the doctor have to test twice in many of the diseases. And for the false negative here, this is more serious, right? For the infectious disease. False negative means that the test say that you are not infected, but you are in fact infected. right? So some of you may have heard the news from US early on that they have problem with testing. Why is the country as big as United States has the problem like that? Because earlier in the infection period, there is like the distribution of the invention, the use of the test, and they found that the test in US that they have, the protocol they have, is actually create a lot of false negative, and that's bad things actually, obviously. So they struggle with the earlier tests to find a way, and it turns out that the better way comes from you get the kind of viral strain from China, creating the things called RT-PCR, yeah, by cutting the DNA into strand and then amplify it to view that there's this exists in this strain. So this is the same one, right? So we are not talking about that, but right, you can see that here. This is the way that you can evaluate the results, right? If the values are in here a lot, then that means it's good, right? The value in here, that's okay. You can predict that customer would not buy and they didn't buy. So yeah, okay. But having true positive is good. False positive means that you waste your resource, right? You would waste resource in coronavirus testing. You mean you waste resource to treat people who are not really infected with disease. False negative, in terms of customer, would means that you lose the chance to sales. So that's the false negative. Okay, so this is the confusion matrix. To put a name in, this is called confusion matrix. Okay. Right, confusion matrix does not evaluate the whole thing. So you need to have better measurements, because confusion matrix will tell you like a big picture that this is the way that this is correct and it's not correct. But you need to have like a matrix to measure that it is good or not good, right? The way to do it is to evaluate these precisions. And recall, precisions means that you can accurately, the model can accurately predict the results. That like if the model say yes, then it will be correct. That's high precision. Low precision would mean that the model say like 10 times yes, but mostly they are wrong. That's low precision. So this is accuracy over the predicted case. Come from TP. This is TP. This is FP, TN, FN, right? It's come from TP divided by TP plus FP. If you take a look at the right hand side here, you may understand it better, right? Suppose we have the cases in the dot here, and the fill dot, right? The black dot indicate the case that you want to predict, like coronavirus, those who have the disease. In the say white dot, it's not actually white, it's the not fill dot circle here. These are negative cases. Then let's say the model predict the middle. Good model would cover the left hand side, like good model would cover this left hand side. But well, life is not that easy, so the model would have problem doing that. So let's say the model can do just in this circle. You have the green here as true positive, TP. And this is false positive. The outside here is false negative, and this is true negative, right? So precision would be this one, right? Precision. That is, it is the proportion between the semicircle, this green semicircle, over the entire prediction, right? The circle itself. So that means if the model is accurate, it's precise, then it should be every time it predict, it is correct, right? That's precision. Another measurement is called the recall. Recall can be thought of as completeness. So recall here indicate the percentage that you would cover the case that it have been. So think about recall in terms of coronavirus testing. That would means you have the case cover for everyone that have virus, right? Which now is on the doubt, and because our number is quite low. Never mind. So this is the precision and the recall. Okay, these two can be used to tell whether the model is good or not. High values mean good, but most of the time precision and recall would be the trade-off, right? You have high precision, you would have low recall. Think about a person, right? You have that one person that tend to not speak, but every time that person speak, it's always correct. High precision, low recall. But you may have a person that have high recall, participate in every event, not missing once, but low precision because mostly they are wrong, right? So this is precision and recall. You want the model to be high precision and high recall, both of them, okay? So there's this measurement to combine both, because when you train the model, you might just want to look at just one value. It's called F measure or F1. This comes from precision time recall divided by precision plus recall, and then time 2. Okay, you get the F measure. All these will be value between 0 and 1. Okay, let me clear it. Right, to evaluate the results, you can do it by using this confusion matrix. Oh, I forgot, but to do that, you need to use library. I don't know if you have installed a library yet. Maybe not. That library is called the Caret library, and I did not install this as well, so I will have to do that as you did. Install packages Caret, not carrot though, Caret. Then wait for a while, right? Because this is a large package. This package contains a number of useful libraries. Right? It contains the function allow you to do the cross validations to evaluate the model, and others. So it's done already. So let's go on. Need to load the library Caret, and then in this library there is a function called confusion matrix. Confusion matrix. The confusion matrix take in the we can look at the help first. In help, it tells you that this confusion matrix take in data, reference, and positive, right? Data, reference, positive, and mode. Let's put in data means the predicted data that we have is res C. The reference is the actual one. It's bank data, the size Y. And positive mean the positive class is the yes class, right? And the mode, because what we want is we want to know precision recall, PREC recall. Oh, I need another library. Install packages E1071. Done. Right, then confusion matrix. Right, it gives you this. It tells you that the model looks like this. I think there's something wrong here. It's too low. Let me check. Let me correct that. Precision recall. Yeah. The model is not that good. So that's the case, because we have only 2 variables there. Right. It's already okay. So it gives you this that okay. For this one, you get the confusion matrix look like this, and the accuracy. What is accuracy? This accuracy comes from true positive plus true negative divided by true positive plus true negative plus false positive plus false negative, or the total number of cases. So you get the true cases divided by the total number of cases, and then you get the accuracy equal that. What is the problem with accuracy? We will take a look at this problem later on in our last lecture on the evaluation. So for now, take my word here, accuracy is not good because you get a lot of no, and it doesn't matter. Predicting that this person doesn't accept the offer does not matter here, because you want to know those who would accept, right? So you can guess that those who not accept would not be good case. You want to know those that are accepting the offer. But you can see that precision here is only 24%. Recall is only 10 something percent. It's very bad model here at this stage, right? But nevertheless, this is how you evaluate the model using confusion matrix. Okay. You can create model with more parameters to see whether it improves the results. This is done in R by using dot, right? Dot represent every variable in the dataset except the left hand side here, right? Except the left hand side here, which is Y, the response. Okay, so we will create a new model using all variables and take a look at the result again. Okay, let's switch to R again. I'm going to create a model 1. This is the GLM of Y tilde dot. The data is the bank data, and family is binomial. Then summary model 1, right? Okay, you can see that there are a number of variables associated with that, not just job, marital associating with that, days, months, and then other things. Now, next would be to evaluate the results. I use res C. This is factor of predict using model 1, and the data itself, bank data, and type equal response. And then we can make this and evaluate this. Okay, by putting in more variables, all right. Oh no, sorry, wrong here. No, this should be res. Sorry, I did it wrong here. Should be like this, res. Let's see, confusion matrix. Okay, by include all variables, now the model performance improve, right? You can see that you have the proportion of yes and yes, right, predicting correctly much more than now you have covered the case of yes, a lot of case of yes, and the chance of making wrong prediction is not like you get like only 10% correct. Now you get 50% correct. So when you take a look at precision and recall, you get precision about 0.5 and recall of 0.675. How does it come by that number? Let's looking at this. Say 3572 divided by 3572 plus 3447. This is 0.589, right? So you know that here, if you take this number, this is the true positive, and this is the false positive, divided by true positive or false positive, you get the precision equal 0.5 in this case, right? And recall as well. So for the recall, we use this true positive, right? and divided by true positive plus the prediction no false negative, or I would say you can think of this as the total positive case, total yes, right? Total number of yes, and this is recall. Right, now you have precision and recall between the two here. Let me clear that. Okay, let's move on. Okay, and the result is better by using more variable. Okay, you get better results. However, that's still an issue, right? In terms of machine learning, what I did in the last two lectures were not entirely correct, because we use the training set to test the model, and that's not good because it can lead to the overfitting, and the model just fit to just that particular data set. Imagine this: if you read a book, just one book, memorize it by heart, and then you kind of learning everything through just that one book. When you encounter the problems, if you cannot apply the knowledge learned from the book, but you just memorize the book, you just memorize it, like memorize my lecture, and then go into the exam without understanding that, you would not be able to explain, right? And I ask you to explain a lot, right? If you are not able to explain, that is actually overfitting. Okay, so in actuality, when we want to in the actual setting, usually we want to separate the data into training set and a test set, or we can sampling the data and training set out, and you can have the test set as the remaining, right? So this is done, it will be done in the next week. I do that here as well. Okay, yeah, we can do it here. So we can separate the data into two parts. First part for training, second part for testing. Okay, so what I did here is to like sampling the data out, bank data train here, sample frag with 10%. I use it to train the model, and then I use the model to predict the whole data set. This is not entirely correct. The correct way would be like separate it into two parts, and I'll show you the way to do that next in the next week in the decision tree, and we will take a look at the method called hold out, that you hold one data set, one set of data to train the model, the second set to test the model. But for now, well, let's do sampling and then train the model again. Well, never mind, we can just look at this. This is for this one, I sample the data, 10% of data, and then make prediction based on that. And you can see that the results are not that different, because you kind of creating representation of data by sampling it out, right? You learn that in the Monte Carlo, in the sampling of the variables, that if you sampling it more enough, large enough, then the data would represent the entire population that you have. Right. Okay, so this is it for today. Your lab today that you have to submit next week is to create a logistic regression model that predict the class. This is the data, the credit approval data set. The credit approval data set is the data set of like customer apply for credit, like credit card or house loan. So let's take a look at the data, and then here, credit approval, I can share that to you. Here the data set. Note that there is no header. Find out yourself how you can read the data without header into R, right? It's just one parameters. Okay, you have here the first. So it's not A16. Sorry. Oops. Oh, wrong button. Let me share again. here. You have these value. There are no annotation on what types of value they are. So usually sometimes when you deal with the data in hackathon, in a lot of company setting, you would not know what that data are, so, because depending on the strictness of the organization. Okay, and the class that you need to predict is whether positive or negative, right? Positive means yes, negative means no. So you are predicting whether you would approve or not approve that credit, right? So instead of so these are the data from human, right? Human judge from these data. So it's GP or MR here. They are just category, but they are sensor, right? Replacing with some unknown value here. So these are the results of human judgment, right? We are going to create a model learning from this example. So the model could capture the pattern that human make judgment, and we create this model out so that later on you can create application that customer can submit the data in, and then it will decide automatically whether to approve or not approve that application. Right. This is actually AI, right? Because you are creating the artificial intelligence in a way that it learns from the data, and then it captures the pattern in the data and make prediction, right? Okay, and also they are here. These are the unknown data, right? Find a way to correct that by your own. And next time when you turn the results in, I want you to justify your decision, right? Many of you asked me in the last exam on what you should do, or what should decide between the two choices. Make decision and choose one. Justify your choice. That's it. That is what I want. I want you to make justification by your own and then explain the reasons underlying that. This as well. So my work that I assign to you is only that. Using the dataset, prepare the dataset for modeling, and build the model and make prediction, evaluate the result. Okay, just that. All right. The remaining decision are your own. Right? Make decision, explain the decision, and submit your report to LEB2 next time. Okay. Any questions on either the lab, the class? For the score, wait for tonight. I will put in. I actually have graded them all, but have not put in into the file yet. Any questions? If you have questions, either from reviewing the video afterward, or having questions right now but not what to ask right now, you feel free to put it into the groups. All right, and I will answer the question that when you know the score, if you want to know how you did wrong, that has to be queued, because usually you can view this. I can show you, but it will be a little bit difficult to show you here on how your score is. What are the problems there? But mostly I would say that you either make mistake in the choice when you did that, because my part that when I look at the grading in terms of the answers, most are fine, right? Most are fine, right? You get like 10 up, right? 15 or but there's only one who get full score. Other than that, well, you get kind of the score downward. But if you want to know how you did wrong, you can ask me online. I will show you how you did wrong, but that would be individually. Okay, I will not do the class like this. So it will be one by one. So just send a message to me later on for that. Formula like in GIM, like y tilde dot. Right. In R, formula. So your friend asks, can you explain about formula in GLM like y tilde dot again, please? In R, when you create a model, you need to give the formula. Formula explain the relationship between, like this one, relationship between the thing you want to predict and the input, right? Or you can think of it as output and input, right? This side, this is the response you want to predict, or the output you want to predict, and the right hand side, the input, right? You can specify it in like job, right? If you write like y tilde job, that means you want to create just one variable, right? So job, you use job to predict y. If you create it like this, job plus age, then it means you use two variables. Like last time, you can always do this. If I have like salary, which I don't have here, let's say I have, and then I put it in star and then age. From last time, you know that this would result in combination, right, between variables, like salary alone, age alone, and salary times age. If you use dot, right, y tilde dot, this would mean y and the all variable except y. All right, so this is the meaning of dot. Okay. Any questions further? Play around with this with the lab that we have here. You can try to repeat what I did here by yourself, and also do the lab, right? When you do the lab, you understand it better than just listen to the lecture alone. Right? So if no more question, let's stop here. We still have class next week, although in the original plan there's no class because of school close, but we will still have class next week for this, because there are any close anymore, and we still have online lecture like this. Next time we'll do classification again, but in the nonlinear model called decision tree, right? Decision tree is a model that is quite famous because it is quite powerful in identifying a class, a lot better than logistic regression here. And it will be the first step toward a more complicated version of tree, like random forest, boost tree, if you want to study about advanced machine learning afterward. All right, so let's stop here, and I will upload the score tonight as well as the video as well. So this is it. Hope you guys are okay with the lectures. If you have questions, please ask. Otherwise, please take care and stay safe, and see you again next week.